So, what we are going to continue our study action of concurrence. And now we are going to study the implications or the consequences of that action of concurrence. How we can have various theorems and subsequent results which might be useful. You might have studied in the class like concurrent triangles, similar triangles, SSA.
Yes.
So here we are going to make it more rigorous with the definitions, with the basic 5 actions: action of continuity, action of confidence, action of purpose. We have different actions. Within those 5 actions, how we can model it, or how we can formulate the general postulates of Euclidean geometry in the algebraic sense. So this was also. So today we are going to see what are the consequences of the action of concurrence. Consequence means in the sense that you are using the deductions from actions corresponding results. That's it. And those deductions generate, you can say, proofs, or they can generate proofs, or they can generate results called.
Yes, sir.
So, for example, if AB is congruent to A prime, B prime. If A is congruent to A prime, B prime, and the segment AB is congruent to itself, so and AB is congruent to itself, then AB prime is also congruent to AB. So if AB is congruent to AB prime, AB is congruent to AB. This is AB prime, A prime. So AB is congruent to AB.
A prime, B prime is congruent to A prime,
B prime is congruent to A prime. That's simple as that. But intuitively it helps that once you try to imagine AB and AB prime are two different line segments.
Yes, sir.
You are trying to make a relation of one segment with another segment. So you are transporting it that way. So
Yes,
that congruence relationship has to be understood in that context. So you can extend it to, for example, now if A, B, C, D, so on and so forth, K and L, and A prime, B prime, C prime, D prime, and K prime and L prime, we two series of points on the straight lines, A and A prime. So if we construct two straight lines, A and A prime, on those two straight lines we have
these segments,
set of points,
points,
respectively, or correspondingly. Then two series of points
are congruent to
are also congruent.
yes,
Also, they are also congruent. They are also congruent to one another. That's the point. So now we have a following set of terms from this understanding. We have this set of term 9, for example. If two congruent series of points A, B, C, D, K, and L, and A prime, B prime, C prime, K prime, and L prime, there are two congruent series of points, also arranged that B lies between, B is lying between
A and C.
or A and D
A
or
and
A and K or
A and L.
In the same way, B prime is
B
between
prime
A and
is-
C, A and K.
Yes, sir.
So this is the thing. Then the points A prime, B prime, C prime must arrange in similar. So your B prime also lies. So what is it? So if A, B, C
Yes, sir.
is a number line, it's a line segment. On that line segment, there are
These points.
these points. So if some point B, for example, is lying between A and C or A and B,
Yes, sir.
but since this line segment is congruent to this line segment, so correspondingly, the corresponding point B prime should also lie in the. We said that the given line segment is congruent to the another line
Another
segment.
line segment.
But that line segment is congruent with its own self.
Yes, sir.
That congruent line segment should be congruent with the corresponding line segment. So the points lying on that segment should be congruent with the points lying on the corresponding line segment. So this means if a point lies between this point, so it should exactly like B prime,
B prime should be
and
lying
B prime
in.
should have congruent resultants or wherever this B will lie,
Yes.
corresponding B prime will also lie between these 2 points, corresponding points. So this is what we want to see. On the same thing, R and this, then so B lies in this. So in similar manner, if angle HE B corresponding, so basically we said the angle is formed by 2 line segments.
2 line segments
which are
extended from one side.
which are extended from the points which are not lying in the same straight line. So this is the way we define angles. Angles, how do we define it? Remember, angles we define
As made by rays.
angles defined as powers of 2 different straight lines. Powers of 2. So in the equal point, 2 distinct half rays. Line.
Yes.
So you can extend the same logic to angles. So 2 angles having the same vertex. So before coming to vertex, so if angle HK is congruent, if it's congruent to H prime, K prime. So this means that according to HK is congruent to H itself, it follows. So if it is congruent to this angle.
This angle and this angle is congruent to itself.
This congruence is congruent to
This.
this angle.
Yes, sir.
So you can construct an angle HT and you can have a corresponding angle lying in the same plane
Which is congruent
which is
to-
congruent to these
Yes.
this angle.
Yes, sir.
But from this logic, you can say you can construct an angle HT and HT prime are congruent
Yes, sir.
to one another. To one another. So we are going to use these facts to certain other facts. Now we have definitions. Definitions means this is 2 angles having same vertex and one side is common. While the sides not common from a straight line are called supplementary angles. You know what is supplementary angles? We take supplementary angles as those angles which have 2 angles having same vertex and one side is common. While the sides not where the sides are not common. So we can say 2 angles having same vertex, and one side is common. While the side not common from the straight line are called, the sides which are not common from the straight line are called supplementary angles. They are called.
Supplementary angles.
So you just remember this fact. So supplementary angles are those angles which are not having common vertex. 2 sides from the straight lines are called. So let me first same vertex, and same vertex, and one side common. While the side not common for a straight line, and it's called supplementary angles. So two angles, if they have common vertex, and whose sides form straight lines are called vertical angles. So vertical angles, and you know from learning of the earlier classes that an angle which is congruent to supplementary angle is called right angle. So you can see like this. Angle congruent to the
Supplementary angles are right angle.
Now, these are definite definitions. These definitions and this understanding will help us in a lot of things. For example, now if you go to two triangles, and those triangles are made of constructed from those segments, line segments,
Yes, sir.
in a given plane, and they are intersecting line segments. They are intersecting
Intersecting each other. Yes, sir.
Yeah, they may be constructed as lines which are not parallel.
They're
Which
not-
are not
yes.
parallel in a given plane. So if we have two triangles, ABC and A prime, B prime, C prime, are said to be congruent to one another, then all the following congruences hold. So now we come to those actions like SSA, SAS,
Yes.
congruent triangles.
Yes.
So this way of formulating it is like if AB is good, is one side is congruent
Congruent to other side.
in the same way AC is congruent
A prime C prime.
to, is the BC is congruent to.
B prime C prime. B prime C prime.
So from this and you can also have angle A is congruent to angle A prime, angle B is congruent to angle B
Angle B
prime,
prime.
angle C is congruent to angle.
C prime.
So this is how we can define two
Congruence.
congruent. So here, yesterday we said one important statement. If you remember, how we can transport a given line segment. We can transport a given line segment in only one manner. So here, this is one segment.
Yes, sir.
If you want to make it congruent, so you can transport it only one.
Yes. Parallel to sir.
Parallel. So one line segment can only be transported
Parallel to
on one side.
Yes, sir.
Lifted one. That's the fact. Now, from this understanding of these facts and this thing, so we come to the theorem. Theorem is if two triangles, A, B, C, and A prime, B prime, C prime are congruent, then two triangle A prime, B prime are
ABC and ABC are
congruent. A prime is equal to this. So it's not necessarily you should hold all the angles should be So near A prime, B prime is equal to AB, AC is equal to A prime, C prime. So angle A is equal to angle A prime. So still the triangles are
Congruent, yes, sir.
Our plus SSP.
Yes, sir.
SSP.
Side angle, side.
So here we are going to from the point of how different polynomials with regard to axiom of continuity and axiom of polynomial and how the previous very good axiom of connection. And now he's what the book is trying to show is that it's trying to show that if we have to presume that this there's also called proof by contradiction.
Contradiction.
So if you assume something else,
Else.
so how
Then
should
prove it wrong.
it should lead to contradictions? For example, proof is for example, if angle B is equal to angle B prime and angle C is angle C prime are fulfilling, it's therefore sufficient to show that two sides BC and BC prime are congruent. If this is also distinct, then we can show BC is equal to B prime C prime and two sides are congruent. So what is saying that if this is this, we can also show that this is this, and from this B prime C prime
It's
is
congruent to B plus.
So if you say if it's not that way, let me take two triangles. We will take two triangles like A, B, C, and A prime. B prime and C prime. So one will draw some thing here and denote it by B prime.
D prime, C.
So
Is it so median on B prime, C prime?
So what's the claim? So for example, it is therefore sufficient to show that two sides BC and BC prime are congruent. We will assume contrary to be true, namely BC and B prime, C prime are not congruent. So if you assume that they are not
Congruent.
congruent, it should lead to contradiction. It should lead to how it should lead to contradiction. This is how we are going to see. We take upon B prime C prime a point D. This is what we are doing. Take upon this point D prime.
Anywhere on.
Such that BC is equal to B prime D prime.
D prime.
So we just cut it here in the middle. So we take another point here.
D.
So such that we assume that this is equal to
This.
So if you assume this is equal to this, the two triangles ABC and ABD have two sides. Now this triangle and this smaller triangle have two sides.
Two
Two
sides.
sides and including of one agree. Two sides. That's why we assume BC is equal to AD. Two sides and included angle one angle, this angle agree.
Yes, sir.
So ठीक
C.
It falls from this action to this action 4 action, action of polynomials. So from action of polynomials, two angles BAC and BAD. BAC with this angle and B prime, A prime,
D prime.
this angle are also congruent to each other. So this means this this angle is congruent to
This angle,
This
but
angle.
which is not true.
constant. So consequently, BA prime, CA prime, BA prime, BA prime, CA prime must be congruent. However, this is what I was important. In fact, I forgot it. That we know that an angle can be laid off in only one and only in one and only one on a given side of curve, on a given side, given curve. So it's a geometrical proof. So that's what I'm saying. How can transport a given angle in the congruence? If you have one line segment, you have to exactly transport it parallel.
ठीक है sir.
So an angle can be laid off one and on one. So if you want to make one
Angle,
angle,
sir.
so you cannot do it in many ways. There is only one way you can do it, and that one way you have done it.
Yes sir.
So another way is not allowed.
ठीक.
The way we have defined it from the geometrical construction. Just like there is only one way we can do two line segments, you can only draw one parallel line. So if you want to transport two congruent lines, so there is only one parallel line. So other way is not. So
Yes,
it will be this from this fact it leads to contradiction.
Contradiction.
So this is not allowed.
Allowed.
BC is not allowed. And from this you can indirectly the two triangles are
Triangles are-
this force. So if two sides and angles are equal, means the corresponding angles again is equal. B is equal to B prime.
This
Angle C is
equal to C prime.
Okay. So in the same way, I'll leave it to you the exercise. So and how corresponding to this, both this is theorem point 1 and theorem 10. Now theorem, I'll just give it one. Second theorem one. So if in any two triangles, one side of two adjacent, this was a side angle. This was side
angle.
Now we can have angle side.
Angle.
So if two angles, two triangles, two adjacent angles, and one side or congruent, then two triangles are congruent. What to prove?
Any true?
So again, so you can prove from the same side. Now, here, previously there were two sides and angle, they were congruent.
They are
So it means the two triangles are
congruent.
congruent. Now we can have two angles and a given side,
And again side as well.
adjacent side, and corresponding angles. So still the two triangles are. So
Congruent.
it's also a theorem, or it's a theorem which comes from this thing, which are the implications of consequence of action of congruence. You got the point?
Yes, sir.
So then we also have action of congruence, action of.
These are deductions from action.
Congruence. One was action of congruence, the other was action of order, and action of connection.
Action.
Each action had its deductions.
Yes, sir.
The action of congruence, you can have
These deductions.
These two terms of this congruent triangle.
Yes, sir.
Side angle and angle side.
Side.
What do you point? So this is another way of saying elementary fact you might have studied. That's it. So again, you will just. So theorem 12, you just only take it as an example. Two angles ABC and A prime, B prime, C prime are congruent to each other. They are supplementary angles, CBD and C prime. So should So if there are two triangles, A, B, C, two triangles A, sorry, B, C, another triangle, A prime, C prime, B prime, B prime. So if two angles A, B, C, A, B, C, and A prime, B prime, C prime, are congruent to each other, then their supplementary angles, CBD. CBD, this, and this. They are also equal. They are also congruent. They are also
congruent.
if two angles are congruent, then their supplementary angles. So if A, B, C, so it's not necessarily like a right angle. You can make it like this. It's not necessarily be a right angle. Because right angle will make it more simpler. You can improve general angles. So if this angle is equal to this angle, this means this angle will be equal to
This angle.
this angle. So what is again trying to show is that how he takes the proof lies in, if you take points A prime, C prime, B prime upon sides passing through the point B prime in such a way such that AB prime is equal to AB, CB prime is equal to CB, D prime is equal to DB. The two triangles are expected congruent to each other. It's like this. Moreover, the angles included by these two sides are congruent to each other by the hypothesis. Hypothesis. So it follows from the theorem 10 that these triangles are theorem 10 is which is this one. Theorem 10 is this side angle. Theorem 10. And theorem 10 is this side. So from this, the two sides are equal and the two angles equal, so the two triangles are congruent. That's it. So it follows from this tree that AC prime with a congruence AC prime. AC is equal to A prime C.
A prime, C prime.
AC and BAC is equal to B prime, B prime, B prime, A prime, C prime.
Yes, and BAC.
Okay. So in the same way, AD is AD is and AD prime. AD and AD prime.
A prime, B prime.
Are congruent to each other. It follows from the triangle CAD and
C prime, A prime, D prime.
C prime are congruent. And consequently, CD is equal to CD prime, and angle ABC is equal to angle ABC. ABC is equal to A prime, So from these congruences and conjunction of the triangle follows from this particular angle CBD and C prime D prime.
CBD is congruent to C prime, D prime, P prime, D prime.
What we have done is to show how we have done. We have done it
By side angles.
side angle side.
Yes, sir.
So first we showed this A prime B prime is equal to AB.
Yes, sir.
This triangle is one to
This triangle.
and then from this you show this triangle is one to
This triangle.
this triangle.
And then
from
angle
this
is
side angle, this angle is
so
one
good
to
at the same.
So again, now extending the same logic, we can say that again this was also third. You can also have another theorem. You can see theorem is a sort of deductive proof
You prove from axioms.
from actions. Which may have, which is a consequence of one step or many given steps. A sort of reasoning.
Yes, sir. Yes, sir.
Reasoning of
Certain
many
reasons
steps
on axioms.
to arrive at a certain result. Which would be interesting for us. So there's also something called now thinking where does the reasoning stop? So we have to think where it stops. So in the same way, the theorem is if we have angle HT of the plane alpha, so it's congruent to the plane angle HT H prime, K prime of the plane alpha prime. So, and let L be the half ray of the plane alpha emanating from the vertex HT, because it should be half ray from which an angle emanates.
Yes, sir.
So there always exists plane alpha prime with the vertex of the angle H prime line with the angle such that we can also write this HT is congruent to
H prime great.
So we can always have if we have from an angle emanating from half ray to a given plane alpha, we can correspondingly map or we should always find a corresponding angle H prime K prime in the plane alpha
prime.
Such that the two angles are congruent. Such that the two angles are congruent. Or angle KL.
And both planes should be equidistant.
So it's not as if the both planes should be equidistant.
Is it necessary?
It's necessary.
It is necessary.
Because we are doing things in the Euclidean expression. It should follow the actions.
Axioms of Euclid.
And then we will use both axiom of congruence, axiom of parallelism, axiom of
Yes, sir.
this is the axiom of what axiom of congruence. Axiom of congruence. Again, we can just see the proof again. So and we post. You just attempt this proof at your own place for angles.
Yes, sir.
It's easy. But one result is that, for example, theorem 14 is that if H, K, L and H prime, K prime, L prime be two sets of three half rays. Where those of each set emanate from same point and line the same plane and line the same plane, line the same plane. Then if the congruence is angle HKL, angle HL is congruent to angle H prime, L prime, angle KL is equal to This congruent to angle P prime L prime. And following this congruence at prime at K prime. Now H is congruent angle H prime K. Is also valid. So if we have a HDL and HDL are these sets of 2, 3 half rays. It's not 1 half ray. It is 3 half rays.
3 half rays.
It will give 3 corresponding angles.
Angles.
We are both each are emanating from the same point, emanating from the same point, and line the same plane. So this is the other angle. We would like the
same.
If they make the same plane, then angle HL can find a congruence of this with this angle. KL. And we can have this point H from this point
and K
from this point.
Another ray.
H prime from this point.
Yes, sir.
K prime from this. The corresponding should also go. Got it? Little bit of thinking. So by aid of particle theory, it is possible to do the following simple theorem, which it will help, although it seems to be wrongly in actions. Abhi baat what he wants to say. So what see if you go to Euclid's elements or any book on Euclid's elements, how those actions are stated. So there are. This is stated as an action. This is stated as an
action.
But for in Euclid's, in Hilbert's understanding, he says that it is not an action. It should be seen as a theorem. This is what he says. Although it seems to be wrongly to be an action. So here you have Hilbert's construction of Euclidean space.
Yes, sir.
It has not been classified as an
action. It's
action.
theorem.
It can be taken as a theorem. So that's it. And again, another result is all right angles are congruent to each other. It's also another result. You can just see how all right angles, because there is side to side angles, two lines segments intersecting from emanating from a given point. Two half is emanating from a given point. So you can have a parallel action. You can transport it parallel, exactly in this thing. So from that, all you can reduce all right angles are congruent to each other. So this is so you just from your own logic, and he is using another logic to prove a contradiction also, which you can read from this thing. So if it is not that, if it is not, it will lead to contradiction. Yes. By any one of the previous results, action of theorems. Just to try
which will violate these.
Which violate the previous actions. And you have seen previously results. So you can
yes, I got it.
And another theorem is that that's known as a theorem of congruence of triangles. If two triangles have three sides of one congruent respectively to congruent respectively to corresponding three sides. Three sides of the other, the triangles are
congruent.
What do you see? If two triangles have three sides, one congruent respectively to corresponding three sides of the other, the triangle. Two triangles have three sides, one congruent. So that's as simple as that. Now, one important thing you might, it's useful to at least be conscious of this thing. since it's also self-limited, but so a finite point of how we define a figure. Figure is defined as finite number of points is called figure. Number of points is called figure. And if all points lie on that plane, that's known as plane figure. That's known as
Plan.
plane figure. Now, two figures are said to be congruent. Two figures are said to be congruent when if they are arranged one to one corresponding to the corresponding segments and corresponding angles.
Angles.
You got the point. So if we have a figure is constructed of finite number of points
Points in
and the finite of the number of points which are residing in that plane,
plane.
that's known as a plane figure.
Plane figure.
And if we say that two figures are supposed to be congruent,
Congruent.
this means all the points, all the side angles and all the sides of the two corresponding figures
Figures.
residing in these two
plans.
planes, they should be congruent. They should be congruent with each other. They should be. If they are in one-to-one correspondence, they are in one-to-one. So this is one-to-one correspondence. Means the angle of one plane should be congruent to the angle
Angle
of,
of other plan.
and the side of one plane should be congruent to the.
Side of another.
So the two figures are only said to be congruent if there should be one corresponds to sides as well as angles corresponding to two figures, two planes. So this is a very important property which we exploit in physics, in mathematics, in different branches of geometry. And we explore things, things. How this is also called something isometry. How symmetric properties of figures, how we can translate them in one space to another space. And what are the invariant properties? Those invariant properties can be very much useful. So there, this understanding of congruence really helps. It really helps. For example, we just do and so if ABC, for example, here corresponds to this congruent rule. So third means that if A, B, C and corresponding A prime, B prime, C prime are the congruent plane figures, and T is the point in the plane of the first, there is always possibility of finding P. Point P in the second. So if you find a certain point P, for example, it's residing here or it's residing here, so you should always find the corresponding
prime.
P prime
In between the points.
in the congruent figures.
Figures.
In the respective figures. In the same way, the other theorem is so if A is the other one, P is the other one. So this is the point which is somewhat in between this figure. But if P is some arbitrary point, P is some
Arbitrary.
so we don't know where it is located. Where it is
Located.
So if you know sequentially, if it is here, it should be sequentially like.
Sequentially like it.
But if you do not know where the second point is represented, it's an arbitrary point.
Okay.
The another restriction which is that there should be for the two figures to be congruent, there should be only one. The determination of P prime can be done in only one. Can be done in only one. Got the point? The determination can be done only one. So if P is not corresponding to sequence, it is some arbitrary. But if you, the two figures are congruent, this P has to be the mapping. It can be restricted. There is only one way you can do it. The way between two lines, there is only one point from which you can draw a parallel line on a given line segment.
Yes, sir.
So in the same way, there should be only one way by which we can determine that's P prime. That arbitrary point, P point, which is congruent to this figure. Got the point? So I just
It's very difficult.
For example, there can be at least 4 points. For example, if we have A, B, C, and P, and the corresponding plane figure is A prime, B prime, C prime,
And we don't know where P is.
that is for not like that, then determination P can be done. So you can say conflict P is not that argument with the power motion. First is that there is always the thing is that there is always a way where this point, the corresponding point P point can be formed. And that point can be found in only we can only found point P point so that shall be like this form. So in figure it is contained at least 4 points, not having the same thing. So you can, for example, if you have a figure, so it's 3 sides are there, but you just it has 4th pillar. So it's 3 sides are congruent to some other point.
Yes, sir.
So the remaining thing will necessarily map to the point which is left. So you complete that. That's what.
Yes. That's how P should be mapped into this. Yes, I got it.
This is what he says. This theorem contains an important result. Namely, all facts concerning space which have reference to congruence, that is displacement in space, or by actions of action one exclusive consequences of 6 theorems. So in physics also, you normally have studied translation motion, translatory motion,
Yes, sir.
invariance of space, rotational invariance. So these, how in space we can have some operations which are congruent. We can map those operations in space, which might have different significance in different branches of physics.
Yes, sir.
So how the space can be isometric, or an operation which is done there, it is invariant under rotation, under translation.
Yes,
So
sir.
that is from basic this property of space. If you consider space this way, that we can have 2 congruent space, that is always possible to have a congruence between sides and the angles of one space. We can translate them to some other magnitude. So it's always possible that congruence operation is allowed. Then we can translate this into there are different in any physical operation. If a space is isometric, or if a quantity which is normally conserved, for example, from given isometry of space, we can conservation of angular momentum or conservation of linear momentum follows. If you assume that, there's an exercise in physics also. So how we can translate operations in space? You are very interested in geometry, but this thing, the fact of geometry is
That's in physics also.
geometry and different branches of
Physics.
mathematics as well as intersection in branches of physics also. Again, at the end, we just say the sum of so again, theorem 19, you can see that if 2 parallel lines are cut by a third straight line, then alternate interior angles are
Equal.
Then, for example, 2 parallel lines cut by a third straight line. The alternate angles, alternate interior angles and also exterior, interior angles are congruent. So if two parallel lines are cut by a third straight line, if two parallel lines are cut by a
Third straight line.
then the alternate angles are
Alternate angles and
also exterior interior angles are congruent. Exterior interior this and this they are also congruent. You can just see how it's and correspondingly if the interior and exterior angles are congruent, the lines should be parallel. So if the line two parallel lines are cut by a third line, so interior exterior angles are congruent. So if you assume that interior and exterior angles, so you can go from theorem to action to theorem. Reverse theorem. Okay, you can start from theorem, you can start from action, you can go to
theorem.
from action of parallels, you can arrive at this result. From this results, you can come to back action of parallels. Two parallel lines. They can be by one straight line. Now, one important thing. So we do today action of continuity or not?
Your choice.
So before closing it, so we have another thing is that how to define a circle. This definition is very much so if M is arbitrary point in plane alpha, the totality of points the totality of points A for which the segments M, E are congruent to one another is called circle. M is called the center of circle. M is called center of circle. So what we want to do, if M is an arbitrary point in the plane alpha, then totality of points A, for the segment M is congruent to one another is called circle. For the arbitrary point B alpha, then totality of points A for the segment M. So M is congruent to another segment M. Is congruent to another segment M. Got the point? So then
Yes.
you can form it.
Circle.
So it's if a given line segment is adjacent, it's congruent to its adjacent line segment. Adjacent line segment. And from a given point, from line segment is constructed, you can arrive at the definition of a circle. Got the point? So this definition of congruence is very much helpful. Congruent line segment to its own, there are more than two congruent lines, or you can construct given congruent line segments from a given point, you can arrive at the definition of circle. So from we have arrived at the definition of circle from our understanding of how we define congruence and line segments and points. So this is another way of defining line. So we take 10-15 minutes more.
Okay.
So now. So we have arrived at axiom of parallels, axiom of first was axiom of so we arrived at axiom of connection, axiom of order, axiom of parallels, and axiom of congruence. And now we have added the last one.
Action
By
continuity.
axiom of parallels, axiom of congruence. So these are different. So this is the Hilbert's way of classifying the geometry. 5 actions, axiom of parallels, axiom of congruence. So this is the last part of it. So this action is very much also, if you study real elements or LHC or you study here, they are also very much useful, this idea. And the idea of continuity itself is also very much baffling as well as interesting, or in the different branches of mathematics, physics also.
Yes, sir.
So we say that between 2 points there are infinite points.
Points.
So you should also read, there are some thing called Zeno's paradoxes. As if you have time and see, there are famous questions whether motion is possible or not. For example, in ant, if you divide space into half, the half is divided by half, the half is divided
Yes,
by
sir.
half.
If you
So you
drop a
never-
ball from
you will never reach the point.
yes, sir.
So this is a paradox. But how is movement then possible? How is movement then? So these are questions. So these have been in
If
that
you drop a
era.
ball, it will never reach in the ground.
Exactly.
So paradox.
So, but they have solutions also. These were the same time, this was a philosopher in Greece that time. So these questions are still relevant in different kinds of mathematics. So that's the side one. What the thing is that how can I define action of continuity in this sense? In that we would define this congruences and this thing. The idea of introduction of geometry. We are introducing the idea of continuity in the geometry or rather Euclidean geometry. Which might be constructed of points, segments, lines, planes, and then space.
Spaces.
1 point, 2 points, 3 points. 2 points not, 3 points not lying in the same plane. Will constitute this space. So we based on idea of equality upon actions, relating the congruence of segments and define equal. So if you define something called equal, so this is a person called Archimedes. He might give us some is also associated with this action of continuity. You might have studied Archimedes in school of physics. So if we, for example, if A1, let A1 be any straight line between arbitrary chosen points A and B. So A1 is some arbitrary chosen point between this segment.
Segment.
B. So we can take points A2, A3, A4 so that A1 lies so that A1 lies between A2. So that A1 lies between A and A2.
A and A2.
And A2 lies between
A1 and A3.
A4 lies between A and A5. You can construct a series. You can always construct a series if there are 2 points in the line segment AB and there are corresponding points A1, A2, A3. So you can always construct a point. For example, A1 can be found between A and A2. A2 can be found between A and A3 or A1 and A3. A4 can be constructed from found between A and A5. that succession is there. Or moreover, if you take A1, A2, A1, A2, A2, A3, A3, A4, if they are, if you take them equal to one another, if you take them equal to one another, equal to one another, then on the series of points, there always exists a certain point A and side that B lies between, side that B lies between A and you can always construct a point B which should lie between A and
A N yes sir.
Good point.
Yes.
So you can always find a point which is somewhat. So even if they are small, these segments, line segments, like these points here, they may be equal. So it's always possible to find a point B which is lying between this A
And A N.
Or A and B. Yeah.
B is the last point. Sir.
If they are equal, that's where these
Three.
A1, A2, A1, A2, A3 is a corresponding successive points. So what has, so this is stating nearly this. This is known as Archimedes action, Archimedes.
Sir, how does B lies in A and A N?
How
As
does-
B is the last point on this line. Side.
You are saying that you can always construct A, A1, A2, A3, A4. Want to concentrate on choosing points. Take what is that? No, it's not A also, correct. It's A, A1, A, A2, A, A3, A, A4. It's not A1, it's A, A1, A, A2. It's corresponding A, A3. A,
A4.
A.
But B is the last point.
Oh, B is the other side of this.
Where is A N?
Among the series of points, there always exists a point A, N.
A N is equal to
B
B.
lies between A and N. So,
I think sir, A N and B are equal. A N is the last and B is also the last.
and there always A and B is a line segment.
Yes sir.
So
Line segment.
in this is A1, this is A2, this is A3. No, this is A, for example, A something. That is a point B.
Yes sir.
Because it's a finite line segment.
3.
A and extended.
And A N is extended, and then it's true. It can be.
And what they say that among these five different axioms, axiom of order, axiom of continuity, axiom of parallel, axiom of congruence, we can, and this is axiom of continuity. So we can, axiom of continuity can always find a point which will encompass or cover the previous points which are there in human mind. This is always possible.
There are infinite number of points.
So this is the question. That's why later class you will see number line is very dense. There's always possibility between 2 points. You can add a point.
Point.
Then we also relate to number line.
ठीक
Associate with point and number. This is very interesting in geometry. On try to restrict ourselves to geometry also. Otherwise, extend it to numbers also. When we associate point with a number, we say between two numbers there are
there is number
But that's an analytical way of looking at things. This is geometrical.
yes sir.
Between 2 points there are infinite points.
Yes sir.
But if you associate that point with a number, then between two numbers you can
There
also
infinite
map
numbers.
points with the numbers.
Yes sir.
Then that's the another how construction happens.
ठीक
That's how this is geometry. This is analytical part of geometry. That's why he is a bit excluding this analysis from geometry.
ठीक
Although he can relate them also.
yes sir
That's something called real analysis. So Hilbert is saying that with these actions we can also do action of completeness. Action of completeness means the way we said that if we have two figures, there should be a point which is only in one way. You can extend it with the congruent figure. So it's a sort of like that. That through a system of points, straight lines, and planes, it's impossible to add other elements in such a manner that the system thus generalized shall form a new geometry obeying all the five modes of actions the system of points straight lines. It's impossible to add other elements in a manner the system does general shall be for a new geometry. So you are saying that this system is complete in some sense.
ठीक
Complete means you cannot add something new. If you add something new, it becomes inconsistent.
ठीक
For example, this house is complete. If you add, you cannot add another brick. If you add another brick, it will look hard. You get
yes
out of it. So you are saying that these set of five system of points, straight lines, planes, it's impossible to add other elements in such a manner that a system generalized shall form a new geometry. So no new geometry can be constructed. If you add some new action to these five actions,
ठीक
you cannot construct a new action. It will be something odd. So you can extend it. In other words, the elements of geometry form a system which is not susceptible to extension. So which is not susceptible to, so you cannot extend these five group of actions to some another systems. In geometry can be in Hilbert's construction reduced to these five actions, and these five actions cannot be extended. You cannot add new actions to it. If you add new actions, it will lead to some inconsistency or incompleteness.
ठीक
You should try it. You can
ठीक
that will help you. Can I extend some, change some, any action, any other way, or add any other action? What sort of problems we get? Can we reduce all these problems and reduce self-consistency? So one thing which he is saying is that in action of this connection, action of completeness, there is another action, there is a term that's known as Bolzano-Weierstrass structure, you might study in the subject. And every bounded set is a limit point. So what the gist of that theorem is in the context of this action of completeness is that we can always have So they should necessarily act a point of condensation. They should necessarily act a point of condensation. So wherever you extend some point, there should be some limit point where you can stop it.
Stop it, yes, sir.
There should be existing a point where the point which you want to exist should be subset of that point. It should condense. It's always a possibility. You can condense your point to that point. That is condensation. So
Condensation.
also called Bose condensation. So this is indirectly the theory of limiting points. Theory of
Limiting points.
So when you will study your course in analysis, it will become more interesting.
Okay.
So in Limbert's scheme of things, these are five basic actions. And he, as a part of appendage, this action will also help us in adding our understanding of the
Understanding of
previous
geometry.
actions.
Yes, sir.
What the point? So this is our construction of Euclidean geometry in Hilbert's.
Hilbert's.
Now we are going to step.
Okay.
Stop.
Okay, sir.